Welcome to my video on the triple scalar product. This is lesson number 9 in my vector series. First thing let's do, let's define the triple product here. It's A dotted with B cross C. And this also can be written, you'll see it sometimes written in this notation where it's just in parentheses and they're just put together. So that's an equivalent. Now if we want to write that out in individual terms, that's A1I plus A2J, just writing it out in component form with the unit vectors, A3K. Now we can dot that with, and we know that the cross product can be written as a determinant, so that's IJK, and then the terms are going to be B1, B2, B3, C1, C2, C3. Now multiplying this all out, we're actually taking the dot product. It's going to get a little messy, but we're going to do it. So it's A1I plus A2J plus A3K dotted with, now expanding that determinant out, we're going to get, taking the first column, and then we're going to get B2C3 minus B3C2 minus, and this is the J term, B1C3 minus B2C1. That's B3 minus C1 plus the K term, this is the last column, goes away, and that's going to be B1C2 minus B2C1. Now we know the product, or when we dot I, it's equal to 1, but I dot j is equal to 0, and I dot k is equal to 0. So what this allows us to do, essentially, when we do the dot product here of these two matrices, or these two vectors, what it gives us is A1 times B2C3 minus B3C2 minus J times B1C3 minus B3C1, and then that is going to be the A2 term plus A3 times B1C2 minus B2C1. Now, we realize that that can be written in a determinant or matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. So that's a handy way, which is essentially just A dot B cross C. So we can write our scalar triple product as just a determinant of the three vectors. So that's pretty handy. Now let's do an example. Let's take the vectors A is equal to I plus 2j plus 3k. The B vector is equal to I plus 3j plus 5k. C is equal to I plus j plus 6k. Now we can form the scalar triple product, which is equal to the determinant of the three vectors put together. We just saw that in our derivation previously. So 1, 2, 3, that's the A vector. B is 1, 3, 5, and C is 1, 1, 6. Now if we expand that out, first cofactor is 1, and then we've got a 3, 5, 1, 6. Now about the second column, we get a minus 2, 1, 5, 1, 6. And then the last one is about the third column, plus 3 times 1, 3, 1, 1. Okay, so there's the three 2x2s that we need to expand. So that's going to be equal to the first term here is 1 times, and 3 times 6 is 18 minus 5, so that's going to be 13. The second one is minus 2 times 6 minus 5. That's 1. That's minus 2. And then that was this one. The third one is going to be plus 3 times 1 times 1, which is 1 minus 3. That's going to be equal to minus 6. So if we sum all these together, we got 13 minus 2 minus 6 is going to be equal to 5. So there's the value of our scalar triple product. Now I want to show how the volume of a parallelepiped can be determined using the scalar triple product. So we've got three vectors, A, B, and C, and then we finish out the parallelogram or the parallelepiped to make it into a volume, and we define I as the area of the base, which would be a parallelogram, and N would be the normal vector. That would be B cross C, so it's in the upward direction, so that's a normal vector, a unit vector. And then H we're going to get from the dot product of A and the normal vector. So the volume is going to be equal to the height, H, times the area of I, the base. So it's base times the height. Now the height is just going to be equal to the A vector dotted with this normal vector to the surface, and then that is going to be times the magnitude of B cross C. So we can rewrite this now, factoring out, just rearranging terms. So we're going to get A dotted with magnitude of B cross C, and then that's going to be in the direction of the normal vector or the unit vector, which is going to be equal to A dot B cross C. So the volume of the parallelepiped is just the magnitude of the scalar triple product of these three vectors, which is a pretty handy method of determining the volume of a parallelepiped. Hope you got something out of this video and learned a little bit more about vectors. Thank you for watching.